Welcome everybody to the first lesson of Unit 4, what I'm calling our special derivatives unit. And it's not that they're more special compared to others, it's just Unit 3 was focused entirely on how you learn the rules for differentiation, and now we're just going to add more functions to that. More functions for you to add to your library of things that we can differentiate. And in this lesson, we're going to take a look at exponential functions and logarithmic functions and how to find their derivatives. Reason being, this opens us up to being able to discuss problems where we may have situations with exponential growth and decay. And logarithm functions are also nice for modeling things like populations. So just getting into a couple more functions that have some real-world application to us, so when we get into applications of derivatives, we have a good full understanding of really any type of function that a real-world problem could be modeled by. And so we're going to start with exponentials. And what we want to look at is the graph of f of x equals e to the x, a function that, as we head toward negative infinity, our f of x function approaches 0. And as we head toward positive infinity, f of x follows suit and also goes up to positive infinity. It grows without bound. What would the derivative graph for e to the x look like? Well, think about the behavior of a tangent line anywhere along this curve. If I placed it all the way over here, my tangent, my f prime of x values appear to be flattening out. They appear to be getting closer to 0. Whereas if I start placing them further right along this curve, notice how it's always increasing. So f prime of x is going to be greater than 0 for all x values. But not only is it positive, the slope is getting steeper. It's increasing. So f prime of x is an increasing function. So we've got a positive increasing function that approaches 0 when we go to negative infinity, grows unbounded as we approach positive infinity. Sounds a lot like the behavior of e to the x. And that's exactly what we're going to be dealing with. The derivative of e to the x actually remains e to the x. It's quite possibly the most unique function that we deal with in our study of calculus. It's the only function that exists where the function and its derivative are both exactly the same. And so that is another rule for us to put down. The derivative with respect to x of e to the x is e to the x. The big thing to keep in mind, though, is just like we talked about with trig functions, we're going to always think about using the chain rule with this. This is another outside-inside situation. So when we deal with derivative with respect to x of e to the u, where u is some function of x, what we're always going to have is the outside being e to something, and the inside being that u function. And so with the chain rule, we would get derivative of e to the u, the derivative of e to anything stays exactly the same. It's still going to be e to the u, but then times derivative of that inside function, or derivative of that u function with respect to x. But just get in that habit like we did with trig, always use the chain rule, and we'll never forget it. We have f of x equals e to the quantity 2x minus 3x squared. This entire function is part of our exponent. So this is going to be chain rule with an outside that is e to something and an inside that is 2x minus 3x squared. And so our derivative would be, just like we've been doing with chain rule, derivative of the outside function, e to anything is going to stay exactly the same. So we're still going to get e to the 2x minus 3x squared times derivative of the inside function, which is 2 minus 6x. And usually good notation to put any exponentials, any powers at the end. Our derivative is 2 minus 6x times e to the 2x minus 3x squared. Looking at example 2, f of x equals e to the sine x. Again, if this way to keep track of things is still working for you, keep using it. if you've kind of moved beyond needing to write this outside inside, you should be ready to jump right into differentiating. But we do have an outside that is e to a power, inside is sine of x. And so f prime of x equals e to the sine x, that stays exactly the same, times derivative of sine of x, which is cosine of x. And again, proper way to write that, we're going to move that cosine of x to the front, times e to the sine of x. And it's all done. So yeah, it's just another rule to memorize, but it's not a whole lot extra to memorize in terms of process and problem solving. It's just applying chain rule to a brand new situation. One thing we do want to take a look at is, well, what if I change that base on an exponential to something other than e? Well, it doesn't look much different, but there's going to be a slight difference in how the final result looks. Let's take a look at a quick proof of how we can get derivative of a to the x, where a is any constant for a base. Well, let's think of that derivative of a to the x. Let's think of a to the x as e to the natural log of a to the x, or e to the x times natural log of a. Again, all I'm doing is making use of one property, that e and the natural log. When I do e to the natural log of anything, their inverses are going to cancel each other out. And making use of a logarithm property, where I can take any exponent on the inside of a logarithm and move it out to be a coefficient. And so what I'm differentiating is e to the x natural log of a. And when I do that, well, there's my chain rule. Outside is e to the inside, and the inside is x times natural log of a, where this natural log of a, because a is a constant, natural log of a will be a constant. So differentiating that, we're going to get e to the same exact thing, e to the x natural log of a times the derivative of x natural log of a is just going to be natural log of a, just the same as if it had been 2 times x. And simplifying this back down, notice that e to the x natural log of a and a to the x were the same thing. We're going to get a to the x times the natural log of a, which will be our rule for differentiating an exponential with any base, not just e, any constant base. And working with chain rule, that would mean we are actually going to work with, and here I'll move that natural log out in front just so it doesn't get in the way. We'll have that natural log of a times a to the x. Notice one similarity between working with e to the x and any base, that power shows up again, times derivative of the inside function, du over dx. And so again, any exponential is going to be a chain rule problem. So let's say we want to find the derivative of y equals 3 to the 6x plus 4. Notice how we have outside is 3 to some power, and the inside is 6x. Also notice it's 2 separate derivatives we're going to be working with. So y prime equals, on the first function, we have 3 to the 6x, derivative of 3 to anything would be, still going to be 3 to that anything, times the natural log of this base, because it's a base other than e, times derivative of the inside function, which is 6, plus the derivative of 4, which is just going to be 0. And we'll get y prime equals 6 natural log of 3 times 3 to the 6x. If you use this property with a base e, you would get a natural log of e times e to the x, and that natural log of e would just equal 1. So actually, this is the more general form. And if you remember this form, you can apply it to an exponential with any base. The only thing I want to emphasize is that e will be the most popular base that we encounter. So let's move on to the other function for this lesson. And so the other function we're going to deal with in this lesson is the inverse of e to the x, which is our natural log of x. Now to do that, I'm going to offer you a quick proof using the e to the x function we've already discussed and a few algebraic tricks. So we're going to start off not even looking at natural log of x. I'm just going to use a fact we should already know. The derivative with respect to x of x equals 1. And what I'm going to do with that is I'm going to rewrite that x as e to the natural log of x. E to the natural log of x, e and the natural log would cancel out and leave x, so it's okay for me to make the substitution. But I am going to do this derivative that's on the left side. Because keep in mind, from what we had in the first half of the lesson, this is just chain rule, with an outside function e and an inside function natural log of x. So differentiating, derivative of e to anything is still e to that power, times, I still need to be able to differentiate the natural log of x, which we don't know yet. That's what we're building up to. But what I'm going to say is, e to the natural log of x, well, let's just change that back into what we know it equals. That just equals x. This is x times the derivative of natural log of x, and that equals 1. And if I divide both sides by x, what I'm going to get is that the derivative with respect to x of natural log of x is 1 over x. Now we did make one big assumption, and that was the assumption that natural log of x is differentiable in the first place. Normally, if you have a differentiable function, like e to the x, you're going to have a differentiable inverse, like we will with natural log of x. And so it's not as elegant as e to the x where the derivative was exactly the same, but it still turns out pretty nice that derivative of natural log of x is this simple rational function 1 over x. And again, just like we said with our exponential, treat this as always being chain rule. And it's easier on this one to see that because we read that as natural log of x. So we can already see the composite taking shape. And so thinking with chain rule, if you have natural log of u, where u is any function of x, the derivative of natural log of u will be derivative of the outside, the natural log, will be 1 over the inside times derivative of the inside function. Now when we deal with logarithms, one thing I am going to say, always use log properties and expand. If you can use log properties and expand, you can make the problem much, much easier to work with. So looking at problem 4, and I'll leave those up at the top, we have natural log of cosine of x squared. So we've got an outside, which is natural log of the something, and the inside, cosine of x squared. Notice that this is its own separate chain rule, which we will address when we get to it. But the derivative of natural log of anything is 1 over that thing, times the derivative of cosine of x squared, which would be negative sine of x squared, with its own inside function that we have to differentiate, times 2x. So r f prime of x will be negative 2x sine of x squared over cosine of x squared. And if you're paying attention to this, you should think, oh, sine over cosine of the same input, I can use another trig identity and simplify this even further. That's going to be negative 2x tangent of x squared, and our derivative is complete. Looking at 5, here's one where we're going to want to take advantage of a couple things. One, thinking like we have since power rule, that we can rewrite this cube root of x inside the natural log function as x to the 1/3, but also we have a property that says if I have natural log of a to the b, I can pull that exponent out in front. And we actually already used that in one of our proofs today. So I can actually rewrite this one more time as 1/3 natural log of x. And notice this actually becomes pretty simple because I just have a constant multiplier in front of my natural log of x function. And so f prime of x, I'll keep that 1/3. We'll differentiate our natural log of x function, which is 1 over x. And combining those, we're just going to get 1 over 3x. You can apply chain rule with outside being natural log and the inside being x to the 1/3, but it gets more complicated. We've been talking about this since we started differentiation rules. If you have a way to make your problem simpler, take advantage of it. And just like we saw with exponentials, we are now going to generalize. What if we were dealing with a log of any base? Well, this is going to work similar to what we saw with working with exponentials. Derivative of log base a of x is going to differentiate almost the same way as natural log of x. We're going to get a 1 over the inside function, over the x, but then times a 1 over a natural log of our base. Or you can even think that you're dividing by natural log of the base. And it will be 1 over x times natural log of a. So the only big difference is exponentials, it's times natural log of a. Logarithms, it's divide natural log of a. And so always using chain rule on a logarithm and expanding it to any type of function where u is f of x on the inside of our log base a, we're going to get our 1 over the natural log of the base, we're going to get 1 over our inside function, and then times derivative of that inside function. So we'll get 1 over u times natural log of a times derivative of the inside function. So again, let's leave our rules up there and try to make use of them with these two at the bottom. And for the first of the two examples, we have f of x equals log base 4 of 2x to the 5th. And just be careful on this one. The 5 is not an exponent on the entire inside function. It's only on the x. And so f prime of x, big thing is, it's a log of a different base. So we're going to have a divide by natural log of that base of 1 over natural log of 4 in this case. And then we proceed just like working with natural log. We're going to have 1 over our inside function times derivative of the inside function, in this case, 10x to the 4th. Now, one thing I can notice is the 2 and the 10, when I multiply them, it's going to be a 5. I'm going to be able to cancel out an x to the 4th here. And what that will leave me with is f prime of x equals 5 over x natural log of 4. And in our final example, we have f of x equals log base 6 of 3x times tangent x. That 3x times tangent x should already worry us because that would have to require product rule when we get to differentiating it. Unless we remember a property of logarithms, that is log of a times b, can be written as log of a plus log of b. We can actually split our function into two separate derivatives. Log base 6 of 3x plus log base 6 of tangent of x. And differentiating that now, we'll get a 1 over natural log of 6 from that different base times 1 over the inside function on the first one, which is 3x, times derivative of the inside function, 3. Plus, let's repeat the process on our second function. 1 over, again, natural log of 6, times 1 over our inside function, tangent of x, times derivative of the inside function, secant squared x. What we can do on this one is we can cancel out these 3's. This dividing by tangent x times secant squared x, we'll just think dividing by tangent, divided by sine over cosine would be the same as times cosine over sine, and secant squared would be 1 over cosine squared, and we would end up with 1 over sine of x cosine x, or cosecant of x times secant of x. Let's put everything together. I'm going to go ahead and factor a 1 over natural log of 6 from everything. That'll leave me with a 1 over x on the first term plus cosecant x times secant x. But that does it for this first lesson of Unit 4 on differentiating with exponential functions and logarithmic functions. Just try to keep it simple. The only difference between the e to the x and natural log functions and their more general formulas with other bases is that natural log of a. And all that comes back to is remembering that if it's an exponential with a different base, we will times natural log of that base. Logarithm with a different base, divide by natural log of that new base. If we can keep those straight, and we're always utilizing chain rule for both types of functions, we're going to be in pretty good shape. Please make sure, review and summarize your notes, and when you're ready, let's roll right along over to the practice. And thank you for watching this first lesson of Unit 4.